free booklet showing the new 50 sets in full color. Your copy to line folder, WABD, New York.
The Johns Hopkins Science Review, presented by the Johns Hopkins University and WAAM in Baltimore. This is the Johns Hopkins University, famed for 75 years for its contributions to science and the humanities. Here in its many laboratories, Hopkins scientists are constantly probing into the still unknown secrets of science, which, when discovered, will be translated into benefits to be enjoyed by you, the people of America. Each week, we look over the shoulders of these scholars as they work and catch a glimpse of their scientific research. This week, we tell the story of some great men of science. To introduce this week's program, here is Lynn Poole of the Johns Hopkins University.
Greetings, ladies and gentlemen, and welcome to another Johns Hopkins Science Review. Now, from time to time, we enjoy bringing you the latest developments in science, the latest scientific discoveries as they are made in this country. At times, we like to show you the problems of basic research in which there are no immediate results, but results which show up at a later date. Now, the main source of our scientific knowledge and of these discoveries come from the scientist with the inquiring mind. Now, the scientist with the inquiring mind is the man who looks into every fact of science, questions them, and were it not for his curiosity and his inquiring mind, the rapid advances which we have had in science would not have come about. Now, this week, we would like to pay tribute to a number of men who have had inquiring minds, who have made great developments in science, and who have brought the discoveries that you and I enjoy. We would like to present to you these men, the great men of science.
The first man of science whom we bring you has had a profound effect on the lives of most Americans. Although you may not immediately recognize his name, his work has probably done more to change your dietary habits than anything since the invention of the can opener. Dr. Elmer V. McCollum, world-famous biochemist and pioneer in the science of nutrition, was the first to demonstrate the presence of vitamins in animal and plant tissues. Years of tedious study have made it necessary for Dr. McCollum to use a specially designed reading glass to ease eye strain. He is shown here at his desk at the Johns Hopkins University, where he is now Emeritus Professor of Biochemistry. Born in a small sod house on the open prairie of Kansas, Dr. McCollum has been named one of the 24 persons in North America who has made the most fundamental discoveries in medical science during the past 150 years. He is world famous for finding the first fat-soluble vitamin, now known as vitamin A. In 1922, his elaborate study of hundreds of experimental diets with rats led to the discovery of vitamin D, the sunshine vitamin. In addition, he is credited with being instrumental in the discovery of vitamin B1. The impact of Dr. McCollum's work with vitamins should not be allowed to overshadow his many other important contributions to science. Early in his career, he trapped wild rats on which to make controlled studies of various simple diets. These proved too ferocious, so he purchased tamed albinos from a pet stock dealer in Chicago. The results were so successful that nearly every nutritional laboratory now uses such mice and rats for observation in dietary experimentation. His interest in calcium and phosphorus led him to initiate studies on the physiological significance of many inorganic elements, including aluminum, boron, cobalt, fluorine, manganese, nickel, and zinc. The McCollum-Pratt Institute for the Study of Micronutrients is a testimonial to his achievements and interest in this field. Today, biochemical journals are filled with papers describing some kind of enzyme action in which the initial experimental work was done by McCollum. At 73, Dr. Elmer V. McCollum is still actively engaged in research and is currently developing new methods for separating the component parts of natural amino acids.
This is Dr. John Boswell Whitehead, who at 79 is known as the father of the Johns Hopkins School of Engineering. A professor emeritus in electrical engineering and a graduate of the class of 1893, Dr. Whitehead has profoundly influenced the field of dielectrics, or non-conducting materials. His research, especially in the realm of high-voltage electricity, has won him recognition throughout the world. To him have come the honors in abundance: the French Medal of Honor, the Edison Medal of the American Institute of Electrical Engineers, the coveted Longstreth Medal from the Franklin Institute, the Montefiore Prize of Liège. In 1942, when he sought to retire at the age of 70, he was asked instead to direct a new research project, one completely different from those he had previously done. With typical vigor, he returned to his laboratory and plunged into the fundamentals of the new work. Not only did he go on to complete the specific research required, he also developed a number of new techniques which are today benefiting all research in high-frequency dielectrics. After his graduation in 1893, he joined the Westinghouse Electric and Manufacturing Company, which was then making generators and transformers to be placed at a Niagara Falls power station. He remained at the site during the first year of the great plant's operation. As a full professor at Johns Hopkins in 1910, he acted as consultant during the expansion of the Baltimore campus and at the same time argued for the establishment of the School of Engineering. He invented the corona voltmeter, revised the entire theory of dielectrics, and turned out 4 books and over 100 articles. During the 20s and 30s, his laboratory became a world center for dielectric research. It was there he sought effective insulation methods for high-frequency power lines. Because of his extraordinary memory and concentration, Dr. Whitehead has always been able to approach problems with unusual directness. When he conducts an experiment, he knows almost exactly what the results will be and never loses himself in a welter of data which must later be assimilated and understood. During the First World War, he was assigned the task of tracking down enemy submarines by electrical means. He and his associate, working in a Hopkins laboratory and later from a submarine chaser, devised a way to detect undersea craft by setting up an alternating magnetic field. The war ended before the system could be tested under actual battle conditions, however. Dr. Whitehead's corona voltmeter took shape in 1916 and marked an important contribution toward the measurement of high-voltage electricity. The 12-foot-tall instrument was capable of measuring up to 100,000 volts. The Johns Hopkins University paid tribute to Dr. Whitehead in 1948 when a new engineering building was named in his honor. Still active in his study of high-power electricity, Dr. John Boswell Whitehead is truly a famous pioneer in the field of electrical engineering.
While Dr. Whitehead was winning national fame as a leader among electrical engineers, Dr. Alexander Graham Christie was gaining prominence as a mechanical engineer. Now Professor Emeritus at the Johns Hopkins, Dr. Christie is internationally known for his power plant designs and plans for industrial development. He has designed power stations for many of the major cities in this country and has traveled to England and Australia to advise and design. The big plants at St. Louis, Memphis, Philadelphia, Los Angeles, Cleveland, and Edmonton, Alberta are projects on which Dr. Christie has worked. He is consulting engineer to dozens of Canadian and American public utilities and manufacturing concerns, and is a member of 14 technical societies. He is former president of the American Society of Mechanical Engineers. In 1949, the Society for Engineering Education awarded Dr. Christie the LeMay Medal for Engineering Teaching. An average week finds him engaged in a half-dozen major activities. He may be concerned with patent research for an automobile manufacturer, new sites for power stations, factory smoke control problems, the cost of power plant construction, or the design of such machinery as a proposed coal-burning turbine locomotive. With the power needs of the nation growing so rapidly that by 1970 the estimated output in kilowatt hours will triple that of today, Dr. Christie is in great demand for the planning for the future. The power station at St. Louis is but one of many that Dr. Christie has helped chart. Others include the 90,000 kilowatt plant on the Saskatchewan River at Edmonton in Canada, and the large station at Memphis, Tennessee, designed to serve a chemical company factory. It was under his supervision, too, that the first Alice Chalmers steam turbine was installed at Utica, New York in 1905. Another example of his work is the 65,000 kilowatt turbine generator unit for the city of Los Angeles. The research for the project was done while Dr. Christie was an employee of the Westinghouse Machine Company. The heart of the generator is a complex maze of machinery, which requires hundreds of hours of painstaking labor to blueprint and install. The completed rotor, still a smaller part of the generator, weighs 15 tons and enables the unit to attain its great power. A more recent journey abroad took Dr. Christie to Japan in 1951 as a member of a 15-man American engineering educational mission. The group toured the country for 8 weeks to learn of Japanese educational methods as related to industry. Dr. Alexander Graham Christie, one of the nation's foremost mechanical engineers, and for 38 years an inspiration to the students of the Johns Hopkins University.
There is more to modern living and learning than the exact sciences. We must not neglect the activity in the fields of the arts and humanities. Here is a man hard at work whose name will undoubtedly be familiar to many of you. You may remember it from your college course in philosophy or from such magazines as Hopper's and the Atlantic Monthly. Dr. George Boas, widely known in the field of philosophical thought, takes his place among the scholarly critics of our time. A professor of philosophy at the Johns Hopkins University since 1921, he is a prolific writer on contemporary problems. Like the humanists of the Renaissance, he is a man interested in human affairs rather than in natural science. He believes the only justification for studying any subject whatsoever, be it arts or science, is the importance it has for human life. For more than 25 years, Dr. Boas has been contributing to the bookshelves of America. Such works as Never Go Back, A Primer for Critics, The Greek Tradition, Romanticism in America, and many, many more. Soon you'll be reading his most recent book, Wingless Pegasus, a handbook of art criticism which seeks a solution to the problems which are raised by art in society. As long as man's free spirit is capable of questioning, philosophers like Dr. Boas will probe for the final answer. In his own words, it is the philosophy, the poetry, the architecture, and the sculpture of the Hellenic world which have survived as dynamic forces rather than the mathematics, physics, or astronomy. The humanities are and will continue to be the very foundation of civilization.
From philosophy, we go to the field of archaeology, in which scholars study man's past from the relics found in the ruins of ancient cities. Dr. William F. Albright, chairman of the Johns Hopkins Oriental Seminary, is recognized as one of the world's leading Near Eastern authorities. As director of the American School of Oriental Research in Jerusalem for many years, he has directed many archaeological expeditions in lands whose past stretch back to the Old Testament. In 1950 and 1951, the American Foundation for the Study of Men, under the leadership of Wendell Phillips, sent 2 well-equipped, well-staffed expeditions into Central South Arabia. As chief archaeologist for the expedition, Dr. Albright and his companions journeyed to a little-known, unmapped land at the northern end of the Western Aden Protectorate, which is under British mandate. This area of the Near Eastern world has long been a question mark to scientists and scholars. Before the expedition, practically nothing was known of the material culture of its ancient kingdoms, and even their origin remained obscure. The site of the excavation was Timnah, capital of Qataban, one of the 4 most important kingdoms of ancient South Arabia. Centered in the valley of Bahan, Timnah is about a half-mile long and a quarter-mile wide. It covers an area of about 60 acres. The locality was mapped, surveyed, and partly excavated. Dr. Albright focused his attention upon a mound called Hajar Ben Humaid, located about 9 miles south of the capital of Qataban. The successive towns which occupied this site were represented by some 50 feet of occupational debris, dating back into the 2nd millennium, centuries before the oldest inscriptions hitherto known. Among the most important group of objects recovered in Dr. Albright's excavation was pottery, for there was no way of dating Southern Arabian pottery prior to these digs. The Hajar Ben Humaid site was ideal for this project because the digs were well stratified, with large quantities of pottery preserved in all lower layers, and no appreciable gaps in occupation from the earliest times to the 1st century A.D. The pottery chronology will help establish South Arabian archaeology on a firm foundation and will add to our understanding of the roles these nations played in the ancient Near East. Here is a statue which was found buried in the rubble of a basement in an ancient building. Now known as the Lady of Barat, the figure represents a patrician matron of the late Hellenistic period, about 25 B.C. It is bronze on a limestone base and measures about 45 inches in height. The statue is thought to have fallen from a second-floor parapet during the final destruction of Timnah. The arms broken in the fall were later recovered in the excavation. Here are some of the members of the Kataban expedition. Archaeologist Albright in the helmet, Wendell Phillips, director, on the left, and Bill Terry, field leader, discuss the day's operations. In this scene, the native helpers are shown removing the sand from a digging in the vicinity of the south gate of Timnah. In the foreground is a partially excavated stone replica of a ship. It was probably constructed by a merchant prince who vowed to erect a tribute to the gods if his ship and cargo returned safely to port.
Among the great men of science, the name of Robert Williams Wood must be listed very near the top. As a serious physicist, Dr. Wood is best known for his work with diffraction gratings. The diffraction gratings divide light into a spectrum of more than 100,000 colors. Largely as a result of Dr. Wood's pioneering, gratings are now essential tools of astronomers, industrialists, and the Federal Bureau of Investigation, and are rated the most valuable instrument in physics research. His special diffraction gratings revolutionized the techniques of astrophysical research and were climaxed in an 18-inch replica grating which resulted in a new star discovery. Dr. Wood's first real accomplishment came about while a student in Berlin in 1896. Röntgen, who discovered the X-ray, was experimenting with a focus ray tube, but the rays caused deterioration of the glass. Dr. Wood devised the tube you see here, with a small piece of platinum within it to deflect the rays. German scientists discouraged further work with it, but 6 months after his return to the United States, a similar tube was credited to another scientist and was the forerunner of the focus ray tube still used today. In 1909, 2 decades before infrared photography came into use, Dr. Wood developed an infrared filter which took pictures equally well in daylight or complete darkness. This photo of a tree was one of the earliest taken with his infrared filter. Portraits taken with the filter showed pores in the skin and the system of tiny blood vessels beneath the skin, and they pointed the way to general use by medical diagnosticians. In order to study the diffraction effects on landscape, Wood built a fish-eye camera. The results were the photos you see here, showing how diffraction makes the world look to a fish. He pioneered in the field of supersonics, and during World War I, developed the ultraviolet lamps, now known as blacklight lamps, used in fields as widely separated as medicine, mining, and commercial laundries. The number of his contributions to science may be judged by the fact that he has written 2 books, one of which was and still is a standard text on physical optics, and over 260 papers for scientific journals. On the lighter side, his book, How to Tell the Birds from the Flowers, first printed in 1917, has run through 27 editions, the latest published this year. A favorite avocation of Dr. Wood is that of detective. In 1920, he was called on for scientific study of the clues in the famed Wall Street bomb case. He solved Maryland's Candy Box murder and explained the mysterious death of Emily Briscoe. Later, he joined the FBI faculty as lecturer on the means of violent death. Dr. Wood is also credited with more familiar discoveries, such as the method of frosting the glass of electric light bulbs to modify glare. As early as 1900, Dr. Wood was invited to lecture before the Royal Society of London about his animated photographs of sound waves and drawings of wave evolutions, a process which was, incidentally, the direct forerunner of Mickey Mouse cartoons. These have been only a few of the contributions of Dr. Robert W. Wood, a great man of science. There's one branch of science newer than any you've seen so far this evening. that is not one branch of science at all, but a combination of all of them. We can't show you one great man practicing this science because it isn't done so much by individuals as by groups. It is not a pure science, but an applied science. Operations research people work directly on military operations and apply to them scientific techniques drawn from all the other sciences. We have here Rear Admiral Temple, senior naval member of the Weapons System Evaluation Group, which is the operations research group that serves the Joint Chiefs of Staff. Dr. Jacinto Steinhardt, Director of Operations Evaluation Group, and Mr. E.C. Williams, Director of Operational Research for the British Admiralty. Admiral Temple will give us the Navy's viewpoint on what operations analysis is and how it works.
This is the 10th anniversary of this applied science as far as the United States is concerned. It was 10 years ago, in 1942, that the U.S. Navy set up the first formal operational research group in this country, since renamed the Operational Evaluation Group. The 10th anniversary of this group is being celebrated in Washington this week. Operational research is not simply obtaining information and discovery, as is true of most sciences, but is to adduce facts upon which to base advice and from advice decision. In order for advice to be profitable, there must be a user, and the user must be willing to heed the advice of the agency producing it. This is the status of the Navy with reference to the Operation Evaluation Group. We are the user of the advice which they produce. Dr. Steinhardt, would you care to discuss operational research?
Operations research is difficult to define, but rather easy to understand in terms of concrete examples. The best way to describe it briefly is that it falls halfway between the ordinary military planning we've had for a long time and that kind of engineering analysis that has always been a part of the development of new weapons. The cornerstone of operations research is data. By data, I mean numbers. Numbers which can be analyzed and then applied in analyses of large operations. The numbers that I speak of, for example, are how far and how fast aircraft fly, how many rounds of a particular type of ammunition it takes to produce a kill on a given enemy aircraft. We use these data in order to get numbers that can be inserted into mathematical equations that are quite comparable to those that the physical scientist uses to understand the physical world. If we have numbers to put into them, we can test their correctness and therefore our idea of the operation. We can predict the optimum way to conduct the operation. We can predict what different kinds of operations will be in the future. But I'd like to give Dr. Williams a chance to talk about operations analysis in England because it's much older there than it is in this country. That's where it started before the Battle of Britain.
Yes, we did use it earlier in the United Kingdom than in the United States because, in fact, we had to. The war for us started in 1939. The term operational research was specifically in use at the research station which was developing radar for the Royal Air Force. During the war, we studied operations and weapons, and by studying helped to improve both of them. Theories were developed to explain the facts. This is very important. Operations research is not merely the collection of statistics about operations. And finally, the theories and facts were used to make predictions about the outcome of future operations.
Now is the time for concrete examples of what Dr. Steinhardt and Mr. Williams are talking about. I can think of two if you don't think that they're too elementary. Dr. Steinhardt, why don't you tell how we made Admiral Dönitz think that we had invented a new and deadlier aerial depth bomb?
Admiral Temple, I don't think we have very much time, but in brief, it was the discovery that most of our successes with aerial depth bombs were on submarines on the surface or just diving that made us realize that our depth bombs were set too deep. They had been set deep because the technical people realized that they would have more explosive effect at great depths. However, they were too far from the submarines to go off. It's a long story. That will have to do.
Well, a classic success of the operational research work was the Bay of Biscay offensive against the U-boats, Dr. Williams.
One of the problems towards the end of 1942 was to reduce the number of German U-boats which arrived at our merchant shipping in the Atlantic. They all came through the Bay of Biscay, and the operational research men determined that if we used a certain minimum number of aircraft in the bay, we were bound to sight each U-boat on the average at least once. The number of aircraft was not available, not assigned to the duty, and to take aircraft off another assigned duty at that time on a purely theoretical study was very serious. However, it was done, and the predictions agreed almost exactly with the theory.
We still have work to do in operations research for the military establishment. For example, we have to consolidate what we learned in the last war, have to apply it to new tactics. We have to decide what kinds of new equipment we need, what kinds we don't need. We have to evaluate the value of that equipment which we've already developed.
I think these current problems raised by the jet airplane, the guided missiles, nuclear weapons, the high-speed snorkeling submarines have accentuated the problem. But we do know that Korea has reaffirmed that the operational research is a significant contribution to the services, and as in World War II, we have the operational research people in the fleet off Korea and in the Far East headquarters.
These are the men who have contributed great knowledge to the advancement of science. But they are but a few of the many men of science who, working alone in their laboratories, have developed the scientific wonders which you and I accept almost as commonplace today. It is from men like these, and many others like them, that the scientific knowledge of tomorrow will come. It will come both here and abroad. And for the next few weeks, we plan to bring you some of the latest scientific developments from England. And we hope that you will be with us for the next few weeks, next week in particular, when we greet you from the studios of the British Broadcasting Corporation in London.
The Johns Hopkins Science Review has been honored by an invitation to originate a series of programs by the British Broadcasting Corporation. During the next 3 weeks, the Science Review will present demonstrations of the latest scientific developments by British scientists. The programs will be presented over BBC for the English televiewers, and then teletranscriptions will be air expressed to the United States for showing at the same time over the DuMont television network. The first in this series will be a tour of the BBC studios and a demonstration of the manner in which the British prepare and present a television program. We hope you will be with us next week when the Johns Hopkins Science Review presents the first in its series from overseas, and we watch Television in England. The Johns Hopkins Science Review is produced by Lynn Poole. Directed by Paul Kane. Associate producer is Robert Fenwick. Associate director is Ed Sarrow. Art direction by Barry Mansfield. Your narrators have been Ted Jaffe and Royal Parker. Filmed portions of this program by John Spurback and Jack Ponfield. The Johns Hopkins Science Review originates in the studios of WAAM in Baltimore.
This is the DuMont Television Network. Next, Guide Right, your Armed Forces program.